Yeah, we'll start. So Rainpower was one of the partners in the HydroFlex project. So we're happy that we have the CTO Henning Lysaker here to present a little bit of their development of the Rainpower endurance software and also some of the testing they were doing during this project. Henning, please.
Yes, thank you, Bjarne. Henning Lysaker, representing Rainpower, working in the laboratory, turbine laboratory here in Trondheim. We have been a part of work package number 3, and the result of our work is this Rainpower endurance software program that we are going to present here. A little bit about the background and the motivation for the project. As we know, all turbine runners experience dynamic stresses, and this will vary with the kind of operation, and of course it will be more severe for the high head units that can have higher stresses than the low head units. We have seen from the history that, as Viggo also mentioned, some of these runners have experienced cracks after just a few hours of operation, some after 30-40 years, and some have been lasting for 100 years. So try to predict the lifetime of this is the case. And we have been working for this for a long time. Really, the first experience with the runner cracking was in the 1950s, and in this period we have worked with the material technology, the welding technology. We have been studying the resonance, trying to calculate the resonances in the units, and all of this has improved during these times. But also in the later years, we have seen some units crack. So starting up with this, we see that we are missing the SN curve for the material we are using in our runners. The material we are using and our heat treatment, our welding, we didn't get any SN curve that was valid. And then in this project, where the aim is 30 start-stops, different operational mode of the units in the future, how will this affect the lifetime of the runner compared to how a lot of this runner was designed for operation in the best point. So this is a glimpse of the software program. Out for sale now. This one. So this is a software to calculate the partial damage of the different operational mode of the Francis turbine. So startup sequences, stop down load reactions, and all the loading between 0 to 100% load. You can add in the program, and you can try to calculate then the predicted failure probability. So you can look at both the partial damage and the whole period to see over the lifetime. And this program is generic. You can add any type of SN curve. If you produce a runner in aluminium, you can use the SN curve for aluminium. If you have different types of weld, you can do that. And you can use it for your spiral casing or whatever product it is. It's generic. But of course, in this project, this is the aim is to calculate for the Francis turbine runner. So this is take the reference back to the presentation for Viggo. He had all of these boxes with the failure modes for the oil system and the whole turbine system. Now we are only looking at the runner and this component alone. So this is the process chart of the lifetime prediction. It starts up with prototype measurements at site on the actual prototype. We go into field and measure the strain, the pressures, vibrations, and so on the runner. This one we combine with the finite element analysis, because we are not able to measure exactly in the most stressed areas. We need to correlate to the finite element calculations. And combining those two, we can calculate the static and the dynamic stress amplitudes of the component. The parts that has been most in focus in the HydroFlex project is then to obtain the SM curve, the material data that we need to add in the program, and combining those the calculation of the static and the dynamic stress amplitudes and the material data, we can calculate the partial damage. For instance, of a startup sequence or a stop sequence, what is the partial damage of this operational mode? And if we add also then the operational data, historical, future operation, we can make a prediction for the total lifetime of the component. So I will go through these different steps here. First of all is prototype testing. In this sequence, we are using our flight recorder. This unit is a waterproof unit that has a data acquisition system built in with a battery package, so it will last for 12 hours or so. We can gather data, 32 channels, 4,800 hertz, and we can add them strain gauges, vibration sensor, pressure sensor, temperature sensors, and measure. So typically we assemble this on site, and we do all these kinds of measurements, and this will be the basic. So we have done this on some old runners and some new runners, and typically now, if you get a contract for Statkraft to deliver a high head runner, you need to also to guarantee your stresses and make these measurements just after startup of the new unit. Yeah, and so then from these strain measurements, we can calculate the stresses in the different points. Yeah, so also here on the right hand side, the pictures here. On the lower picture, we have these pressure sensors in the hub of the runner. And we also on the upper picture, we see the strain gauges that is attached to the blades. We pick out some blades that we measure several points for strain measurements. And in this example on the right hand side, upper figure here, we have tested different startup modes. We have the time as the x-axis, and we see we have been adjusting the ramping time and see the effect on the pressure and the acceleration and the stresses in the run. So that is also something we can vary in if there will be more start and stops. We need to also take into consideration the ramping speeds of the start and stop, and also during the operation of the units. And the graph in the middle here is then the stress amplitudes, megapascals, in different locations on the runner, and the x-axis is the generator output. So the upper one here is the suction side at the hub, closer to the hub side. That is has the larger stresses and also higher here at around 40 megawatts compared to the higher loads. So this work takes typically a week's time at site. A lot of preparations, just less than a day for the measurements itself, and but it's a time-consuming process to install all this equipment. But then nothing happens to the runner. This will be you will have the same stresses in the same operational mode at any time. And especially for these high head runners, if there is not so much change in the head variation and the suction side variation pressure, it will very well reflect the operational for the whole future time of operation for the unit. And then we have the results from the prototype measurements. As I said, we have not necessarily been able to measure in the highest pressure or stressed component positions. We need to attach the strain gauges to a flat area on the blade, and typically we have the higher stresses in the middle of the welding areas. So, for instance, here in the picture, in the figure in the middle here, we have the measurement point 40 millimeters away from the band and from the outlet or edge of the blade. And we have several points like this. And comparing the measurements now with the finite element method, we can then interpolate and extrapolate a model that we have the stresses for the whole blade. And so we, from the finite element method correlated with the measurements, we have a stress model for the whole blade. Next step is then to calculate it's a rain flow counting process. You know, the measurements we obtain, it's a different amplitudes, different frequencies, overlays of different phenomena that causes these stresses. So we'll do a counting process of the amplitudes that affects the different regions of the runner. We also will apply a weak link method, then introduced by Herkegård and Kvale. So we can calculate from the local stress we measure in one point to the effective stress and this multi-amplitude system to the whole volume of the unit. So we will calculate for the whole runner based on the measurements. So then into the program, we will add a text file, also for the representative stress amplitude for each operational mode for the whole construction. And together with the SN curve, together with this, we can look at the partial damage for each operational mode. So in the figure down on the right-hand side, you can see an example. The green one here is startup. So the x-axis is representative of the output. And we can see that each cycle of startup had so-and-so partial damage on the unit, comparable to operation at low load, part load, full load. Yes, so that's the first calculation in this. Next, which very much a major part in this project has been to obtain a new SN curve for our material. So this is a 13.4 stainless steel plate. We have welded two parts together in our workshop in Sørumsand, a long piece of material. And then this one has been heat treated together with the runner, and also we have done NDT testing so that we see that there is no failures in the materials above 1 millimeter, which is the normal criteria for us. And after that, we have cut it in pieces, approximately 10 millimeters apart, and made our all our test pieces, specimens for the testing. yeah, I guess maybe all of you are familiar with the SN curve, but this is vital for the process. So I will say a few words about the figure on the right-hand side. X-axis is then a logarithmic scale of the cycles that occurs, typically stress amplitudes in this manner. And the y-axis is then the stress amplitude, typically in megapascals. And in up to 1,000 cycles, we have this low cycle fatigue area, and in between like 1,000 to 1,000,000 cycles, we have this high cycle fatigue, and above this we have the very high cycle fatigue area. Typically, for a runner, there is billions of cycles, so we are operating in the very high cycle fatigue area. And it has been a discussion. Some says that if the runner lasts for 1,000,000 cycles, it will last forever. Is that true? That has been discussed. But we see that for the material testing, that also in this very high cycle fatigue area, that is above this knee point, above the 1,000,000 cycles in this area, there is still degeneration of the material. So there will be infinite lifetime of the material. Yes. So all these tests has been performed also at positive stress. Okay. So we have done a lot of testing, made 118 different specimens with different shapes. Semicircle specimens on the upper left side, different type of notches. We have some smooth specimens on the right hand side, and we also drilled hole in the specimens to visualize material defects in the specimens. So yeah, this was a time-consuming process. It needs to be precise. We need to have them with a nice surface so that there is no defects during machining and so on that will affect the material. We have used a lot of time, or Sintef have used a lot of time with the fixture of the material pieces. A lot of them broke in the beginning when they were fixed in the fixture. So we need to have no effect from the fixture in the system. So we have to really have the high stresses in the most narrow area. And we have also been doing testing in water. We see that the water have a negative effect on the fatigue, both in the high cycle fatigue area and also an effect in the very high cycle fatigue. It will alter the curve both ways. And as you see, we have tested a lot of different material pieces. Some of them are smooth, some of them are notched. And we have also used this stress energy density method to be able to compare it. In this method, you can compare the different notches, the angles of the notches, how this will affect the stress energy density. So yeah, typically you will have a scattered. This is an example of the result, our results in air, and you will have a scattered diagram. This is a statistical test. You see, there is 10 times more circles per. This is a logarithmic scale, so you see the bandwidth of this testing is quite wide. Some of these specimens fails 10 times earlier than the other ones. If you're using the this stress and energy density method, you can narrow this gap, because then you take into account the notches and compared to the smooth surface. Yes. So in this line, in the region on the left-hand side, in the high cycle fatigue area, we will have the curves now for 50% probability, 95% and 5% probability, and also lines in the very high cycle fatigue area. These are time-consuming tests to perform. So the high cycle fatigue area, we have quite a bit of testing. This is testing for a day, 2 weeks, maybe. The very high cycle testing is several days of testing, weeks of testing. We have less points in this area, and that's the real challenge here. We are going to predict the slope of this line until billions and billions of cycles, and a lot of these are runouts that don't break within the time we had them in the machine. So we have few points that has really failure in the long term. So we would like to have more. So this is for the future, to have more testing here. But each sample will use weeks in the test stand, so it will take time to do this. These are the testing in water. The level of the peak stress is lower than in air, and also the slope of the gradient for the very high cycle area is steeper. So there is a definite change in the curves when we go to the testing in water. But as I said, this is just days and maybe weeks of testing. What happens if the runner is in water for 50 years? What is the effect of the water for a long time? Degeneration of the unit. What happens if you add particles hitting the runners, cavitation, and so on? That also can introduce other effects. This is perfect steel. Yes. So compared to other standard SN curves that we have used in before we made our own material test, we see that our tests can withstand high pressure in the high cycle fatigue area, and also in the very high cycle area. These are very good results, and far better than we anticipated and has calculated before. And also the gradient seems to be a little bit lower than we have expected. So then back to the program. If you're using this program, you will add the SN curve, and by default now we add the SN curve obtained by the measurements we have done in the project here. But you can add any curve, and typically we can add with different probability of survival here. And you can add for any other component. We could do the calculation for the spiral casing, for the stay vanes, and all the other components. But of course, as we have seen, there is some more probability for problems in the runner itself. And then we add these results from the prototype measurements combined with the finite element analysis. We also add the file with the fatigue data, which is the really stresses that the stress amplitudes that will occur per cycle or per hour for operation for different power modes. And the program will calculate then the partial damage on this side. So for instance, here you can see that 1 hour operation at 30% or megawatt or you use for the axis will have a larger partial damage than one startup sequence. But this is an example. And as we talked about, no turbine is the same. You need to do this for everyone. So, and this is just an example. Yeah. So after you have added the fatigue data of the unit, you need to then to add the operational log, and you can add for a current runner that you have. You can add the historic data from the transcription of how you have been operating the machine over time, and you can add also future operation. So here we can add these 30 starts and stops, more operation at part load and full load, if that's and check out how will this influence the lifetime of the system. Yeah. So this is also a generic system. You can add whatever you want, and you can add also the accuracy of the x-axis with different columns. If you use one column, you will see the total operational time of the unit, and you can narrow it down. Or if you have very precise data of just exactly operation at this and this output, you can make a very precise evaluation. Yes, and then you can go into this last phase here to look at the failure time. And this one is then the failure probability. And here we can calculate, we can change also this survival probability on this page, 5, 50 or 95%, using the different curves that we added in the SM curves, and calculate the failure probability for different modes of operation. So, for instance, here the black one is a historic curve. If the unit was put into operation in 2004 and it operates until 2012, this is the historic data, and we can add the green line, which is one type of future operation, and see how this degenerates the runner and how the failure probability increases. And yeah, compared to these lines of different yearly average operation. So you can go back and forth with this, add different modes of operation, check how will a lot of starts and stop influence the operation of the runner, how will a lot of operation at part load influence the probability. Yes. So then we have made quite a lot of measurements at the site, and this one is an example for Trollheim power plant, 370 meter head approximately, 127 megawatts. So we did an upgrade there in 2020, and what we typically see now in these measurements of our new units is when this unit is produced and designed according to the proper margin to resonance frequencies. Typically, driva, as Viggo mentioned, failing after a few seconds. It's not necessarily due to the thin blades. There is some kind of resonance problem. So if you have a proper margin to the resonances, and if you have good control over your production process and no material failures, using the program here with these SN curves, you will calculate lifetime far beyond the 40 to 50 years of design life that is normal expected for a unit like this. It will be far, far beyond. So if so then it's maybe difficult to use it, but then you have the partial damage. You can see how much is a startup compared to current just operation in the best point of operation, and look at the differences in this now. So the conclusions here, the wells that we have tested are very good compared with the current SN curves available. The endurance program can calculate the partial damage and compare operation modes, which was the aim of the project, to compare the increase in number of starts and stops. And utilizing these modern design tools, and if the runner is produced precisely and so on, using the program, you will predict a lifetime that is far beyond the 40 to 50 years operation. And we also see that there is a negative effect of testing in water, an indication of more rapid degeneration. But that is an issue. We have not tested for 50 years in water. How is, and going back to the curve here, this is, extrapolating this curve out to billions and billions. This is the clue in this. This is, we should have more data in this. So this is for, back to this one, for the future, we would like to have more specimens tested at high cycle or very high cycle fatigue area. This is very expensive, takes a lot of time, but I think it's worthwhile to do it. So we hope for another project for this. And we also would like to do testing for other types of material, other types of welding processes for the runners that are out there 50 years and had 50 years of operation. We have material pieces from some runners with cracks. We would like to do that, and that is also proposed in the HydroSan project. Yes, we'd like to thank you, Horizon 2020, for the contribution to the project. It has been very valuable for us. All the partners in the HydroFlex project. It's been a valuable project to work together on, and also Philip Roberto, Pietro Fotti, and Antonio Alvaro for the testing and all our supervision in the Institute of Mechanical and Industrial Engineering. So thanks.
Thank you, Henning. I'll open up for some questions from the audience.
There are some curiosity.
Yes.
So nowadays, the Norwegian power plants, they have at least start-stop sequence variation in the operation once a day, at least. So have you diagnosed any failure, fatigue failure in these turbines over the last 30 years? Has there been any changes?
Yeah, there has been. And as Stig also mentioned, Driva and San Marguerite, we have Svartlisen, we have several units, and also for all the producers. So power turbines has experienced cracks in the units, and And there is this High Head Francis project up in NTNU that has been working on this, and all the producers have been working on that. And much of this is related to the resonances, this rotors that do interaction and this resonance frequency. So we think that all of this work, all the measurements we have done on the prototypes the recent years, our new and better computer models, we are able more now to predict the resonance frequencies in the units. Because it will change when you add the runner in water and put it in operation with the narrow gaps, with the ceilings and everything. It's different than just predicting in here. So we have better tools these days.
But there is also, I am a tunnel man. I'm interested on the waterways. So because of this stop or variation of operation, there are some changes in the tunnel system. So is there any evidence that there are some stone flowing with water and they may impact the blades, or only water pressure variation?
No. You know, when we do the measurements on the prototype, we measure the total pressure due to the waterway system and all the effects that is to the runner itself. So these effects on the runner we will take into account in the measurements. But we are only calculating for the runner itself, not for the waterway.
No. I mean, when the water is coming to the runner.
Yes.
So
that is measured.
Not only water comes, maybe that there are some floating small pieces of rocks that may have an impact on
that. That might impact.
Because our tunnels are not very well designed with respect to this too much variation in the start sequence.
Some of
that we have documented with our research within hydrogen, of course.
Yes. Now that's right. So that is one of these uncertainties in this. If you will have rocks or sand coming in due to this rapid start and stop, then you need to account for that. That is not on this research.
So there is a possibility to have more expanded research in this area.
Yeah.
Where we have both the tunnel system and then the mechanical system.
Yes.
We also have some questions from our online audience. So Carl-Michael Högström, just unmute and.
Yes, can you hear me?
Yes.
Okay, thank you. I had a question regarding the model. You said you need a finite element analysis or the model of the runner. Does this mean that the model itself is restricted to this runner only, or can you group several runners to use the same calculation?
I think it will be very prototype specific, this one, Carl-Michael. And also because we are not able to measure directly in the highest stress amplitudes, we need to extrapolate. And to that, we need the accurate model. You know, the shapes of the welding and the radius and all this can affect very much the stresses. So you need the accurate geometry of the unit, and all units are different. So you need to do it specifically from unit to unit.
Yes. Another question regarding the material testing. I was wondering of the effect in mortar. Have you tested with constant force, or is it constant displacement, or have you measured the local stresses in the test material itself, or can you comment on that?
Yeah. No, it's a constant stress for each amplitude, and there is a positive stress on each side. And we don't measure the actual strain for each cycle. it's adjusted for the first cycle, and then it's oscillates in this manner. Yeah.
But do you calculate the stresses based on the force you introduced?
That's right. So we measure the area accurately, and we measure the force.
So have you taken into account the effect of added mass, for instance? I suppose that you have some. I didn't see directly the picture how it was done there, but could you have effect from the water, which create higher forces, which is not affecting the test pieces itself, but you measure an additional force coming from.
Yeah.
Do you understand? Yeah.
Yeah, you know, there will be the water will act on the piece, and when you have this movement, you will have this extra mass of the water to. So that can be an effect in it.
Yeah, I think that there could be inertia forces from the system, water on the level arms or whatever you use to bend or to pull the test pieces that you have to take into account. Otherwise, you overestimate the stresses.
Yeah, it's
Okay.
the basin is quite narrow around material piece, but that could be.
Okay. Thank you.
Ole Gunnar.
I'm just wondering if the system you have made is compatible with these standards that we have been talking about, this FMU and FMI type of things. Have you been trying to implement it in such a standard so we can implement it in any power plant in the future?
I'm not sure if I got your correct Ole Gunnar.
Remember this, the FMU and FMI, the functional mock-up units that we have been talking about, which is a standard way of communicating with the other system in a power plant. I wonder if you have made an effort to try to adapt to such standards.
Not in this project, Ole Gunnar, but I'm sure that there is an easy input and output phase of this program that can easily adapt to the standard, and this one like being a black box in the system.
Yeah,
so
that's the way I understand it as well. So
yes, I think that could easily be done. It's done very easily with input and output files, so I think it will be easy to adapt it.
Thanks.
Björn.
I'm just curious, the operational history data that you show, how much pre-processing have you done on that? How much cleaning have you done on that data to be able to certainly say that you're not just picking up a bunch of transients that you assume are steady state operations?
Yeah, you know, this is different from plant to plant, how the accuracy of their historical data. Some are quite precise, some are not. We have not used the program really for all runners yet. The program is made for this, but we have used it for new units.
Okay.
And played with the future operation week that is built in for historical data.
But there's no, you need to kind of pre-clean the data before you put it in.
You need to make a text file with count.
Yeah.
Number of hours of operations.
Thank you very much, Henning. The HydroFlex project itself, as I said, was financed by the EU's Horizon 2020 program, but it's still, as engineers is heavily involved, it's still running very much within the infrastructure of the HydroSen larger research and development initiative within hydropower. So I asked Liv Randi, director of the HydroSen, to say a few words about the work they're doing on operation and maintenance Maybe some thoughts about the future there. Please.
Thank you. Where should I be standing? Like here or?
Yeah, I think at least close to this microphone. That's easier.
That's the microphone. Okay. Hi everyone. I'm Liv. I think I know most of you. I'm heading up HydroFlex. We have been running since autumn 2016 now. Bjarne wanted me to speak a little bit about the research we're doing on China. Maintenance and operation, yeah. So just to put it in context, we are a quite big center, lots of activities going on very many different projects. You've probably seen this before as well. We are not only working with turbines and generators, we are working with, that's the bragging list. We're working with also with dams and reservoirs, and tunnels, waterways. We have a big bragging list of things we are succeeding with, but we have picked out the research on turbines and generators for now. I guess that's what I'm most eager to hear about today. But there is also quite a lot of other stuff going on in the center. I could, when we're talking about operation, maintenance, etc., I could also spoken quite a lot about both reservoirs and hydropower tunnels, etc. But that's not the subject for today. Yeah, just wanted to point out that we are looking into the core technologies, but we're also looking at boundary conditions that surrounds the hydropower. So that is both water cores, environmental impacts, market services, society and politics, and we're trying to tie it all together also in cross-disciplinary projects. Yeah, but today, let's see what we're doing within generators and turbines. So you should really have asked Arne, which is online, and Ole Gunnar, which is also online, to talk about this, because they would have been able to dig down, deep into the details, and give you colored charts and everything. So we are here now within this work package, and Arne has asked me to focus on these activities. Sorry, you people online can't see, but I'm now highlighting VP2, turbine and generators. And to be more precise, turbine and generator lifetime. That's probably what's most interesting. So when we set out and defined the activities within this project, the idea was that traditionally we have been conducting maintenance in a condition-based way. We have been performing inspections either on a regular term or by demand, but it is more interesting to look at predictive strategies. So trying to see when the equipment will need maintenance and perform maintenance when the equipment needs it. So we have been aiming to try to develop, which is not easy, and test and verify methods and also models for turbine generator lifetime, qualification and estimation. And also trying to develop models that can do continuous evaluation of both aging and consumed lifetime. So we have several different activities that's been going on, and bear in mind that many of these activities started already in 2016. So some of them finished long time ago, and some of them are still ongoing. The very first year is actually carried out in cooperation with the HydroFlex project. So we have a very strong cooperation here, and it's kind of intertwined with each other. Sometimes it's a little bit hard to see what is HydroFlex and what is HydroFlex, because it's the same people, and the people that are in different projects are sitting beside each other and cooperating and using the same equipment. And it's actually great, because these challenges don't live in separate silos. These challenges are overarching challenges, should be solved, you know, across the project. Also, we have had a non-destructive condition assessment methodology for backup generator bars. This was a literature study that was delivered 2 years ago almost. And that work was actually extended and continued with a postdoc that is still ongoing. So the postdoc has then carried out experiments and simulation, has been looking in how to develop non-destructive condition assessment methods, looking at the backup stator bars and the effect of new stresses on old insulation designs. We hope that the postdoc will be able to deliver and complete next year, second quarter next year. And so far, I think we started 2021, autumn 2021. So I don't think there are any publications yet. But
December 2021.
December 2021, yeah. So that
should be Q4 maybe?
Q4, okay. Arne, if you can hear me, you need to update the project plans.
I can hear you. Can you hear me now?
Yes, we can hear you.
Yeah. I muted the microphone. Okay.
Okay, we need to update the project plan here. But it's the postdoc hasn't been working for that long, so we're still waiting for some results now. Then there has been some more literature studies. There have been expert groups, and the report was delivered in 2020. Not quite sure what they concluded with, but I guess if you want to know, Arne can fill in afterwards.
Yeah, it was a survey on the temperature. Let's say how fast the temperature rise and decays then in let's say load changes for generators. So they were collecting information from several power plants.
Okay. Thank you, Arne. Also, this next activity wasn't given a very big budget, so the level of activity is quite low. Fault simulation, trying to introduce artificial faults in hydropower equipment. But I think there are some more activities going on there in other projects. But in hydro, then it was a very small budget and not much activity going on. But in the next one, electromagnetic analysis, online fault detection, we have Hossein, and has been working. I guess you have. If you haven't heard some of his lectures, you really should go online at hydrosen.com and do so, because that is very interesting research. The idea here was to use non-expensive equipment to install listening devices within the generator, introducing faults and using magnetic patterns to detect which kind of patterns you will find if you have this and this fault introduced in the generator. So the idea here is to be able then to detect a fault before it becomes a problem. So that's really predictive fault detection. We are super happy because we have received 2-year verification project from the Norwegian Research Council, came in August, which will enable us to actually bring it forward as the innovation that it is. So the verification project is starting now this autumn, and it's really interesting. So we have industry partners that is very interesting to start utilizing, implementing the technology. Have to say, it's not hydropower producers or turbine producers. It is aeronautics, as far as I know, but nevertheless, implementation is implementation. Yeah, and of course, many master projects has also been conducted associated with Hostein's research. I just had I think it's important to look at the impact that we're hoping to achieve. Avoiding to operate components under conditions and patterns that will make them age faster. That is something that we're hoping to avoid. And also to be able to estimate lifetime of existing components to avoid too early or too late replacement of components. We know that the hydropower industry would like to have this technology, but it's quite a long way to get new technology implemented, because it needs to be field proven and I need to trust it and all that. But this is what we're aiming to do. Yeah, cutting costs, reduce operational costs, etc. Yeah. So this is what we wanted to highlight when it comes to operation maintenance related to generators turbines. Anything, and we need to ask Arne first. He's sitting in his. Do you want to add something, Arne?
You can also say that we had another associated project called HydroStator on let's say monitoring and detecting faults in the high voltage insulation of generators using several type of diagnostic methods. And that was closely coordinated and with the activities in this project, and that was concluded this spring. So the report from that project will be available for all participants in HydroSend.
That's very good. So make a note of that.
Thank you very much.
Thank you.
Leandre. Any questions? Thank you. The idea with this workshop is partially to look back but most importantly is to try to look forward and try to investigate and initiate new research ideas. And I hope that afterwards we'll have a bit of a discussion from all participants, both physically and online. But I first try to make a few input and discussion points. This title is maybe a bit cryptic or even maybe a bit ambitious, but I'll come back to that title afterward as this mechanical degradation Lyapunov stable. I'll come back to that. But first, a bit of a brief historic review, because a lot of this work puts itself into a long continued effort within the hydropower industry to try to move from building new plants to maintaining and managing existing plants. This is the front page of a small brochure that we have. Sintef Energy and Energy Norway was financed by the Norwegian Research Council to try to review some of the research that was done. This was given out in 2011 or 12, I think, marking the 20 years of research and development within hydropower maintenance. So you can feel free to ask me if you want a copy of it as well. And we did this together with Sintef, in particular, Eivind Solvang and myself, and we tried to look at some of the research projects that had been going on within the business and within the hydropower industry. Starting back, I mean, this, as I said, this started very closely tied into the launch of the new energy law, which really marked the change from a very regulated power business to a much more market-based industry. And of course, it's very interesting today to see the current discussion, because actually the liberalized and open market was developed in Norway initially, and then it's expanded to first to the Nordic countries and much later to the European countries. So we have a much longer experience with the competitive and open market than most of the European countries. But already from the start, it was focused on initially on just maintenance management, and then more and more development focusing on risk and failure modeling and developing of analysis environment. And latest was with this Monitor X, focusing, that has been mentioned also, focusing on the data harvest, data collection, and starting to use more sophisticated statistical models and machine learning. And a lot of you who are involved with operation and maintenance may be familiar with this failure model that was developed and also in close collaboration between Sintef Energy, but also Professor Jørn Vatn that was mentioned earlier, where we have these different conditions classified as condition 1, 2, 3, and 4, and then introduced to this fault, where a very, very general description with condition 1 as no sign of degradation, and then condition is critical at level 4. But then that is within this what was called a handbook for power production. That for different components, that's more detailed description on what does actually these different states or conditions mean for in terms of corrosion, in terms of cavitation, in terms of runner cracking fatigues. And exactly the same is used. Unfortunately, for the civil part, dams, somehow the scale starts with 0, but again, and goes to 3. But again, for concrete dams, for rock-free dams, etc., you have the same in the handbook. So when we're doing the inspection and assessment that's required by the regulator, NVE, again, we can use the same scale to say something about the condition of the equipment. And a lot of the power companies, they are at least partially collecting this condition data. And then this model was extended, where we have indicated this probability distribution within these different within these different states. The idea is that you can use these, consider these residence times, T1, T2, and T3, etc., as a probabilistic variable. So here comes this thought of this Markov chain. So you have, that was mentioned by Viggo earlier also, that we have this chain of events where you have moving from one state to another. It's integrated by this curve. And a lot of the theoretical framework for this modeling was described in Thomas Welte's PhD from 2008. And this is developed a modeling framework and a computational framework that's much used by power companies to do at least investment and evaluation of different options for refurbishment. Back in 2003, so actually earlier than this, I was charged by Statkraft to develop a model to say something about how different operating patterns impact the cost, maintenance cost. They had experienced around 2000. We had maybe the first really high peak price incident after the new energy law was introduced, and they have experienced a marked change in operating pattern, and they've seen that turbines that were operating 15-20 years without any problems, after a very short period during this high peak season, they were so this high price season with very aggressive operation, they were discovering cracks on several runners. So this is again a very heuristic model. I mean, it's based on a similar framework that Henning was presenting, but much more heuristic, and then trying to just look at simplified models for the different component or partial degradation models, and then using a heuristic model for the impact of different operating patterns. But like any other field of science, the operation and maintenance field also had their fashions, and it was mentioned one of the buzzwords at the moment is this digital twin, trying to model and actually different, let's say, fields or areas of research. They have changed a little bit with the nomenclature. So within some this, again with this system modeling environment, they're talking about 3 levels of accuracy or resolution here, where they are talking about the digital shadow. The digital model, which is the one-way connection, where you only build up a 3D model with a 3D physical representation. So it can be a finite element or whatever, how you do the computational. And then you have a digital shadow, where ideally you are running this in parallel, getting real-time data from how this, so you're actually running your digital shadow in parallel with your physical object. And that's probably one of the future, let's say, goal of the Grunnøy project, when we can harvest this real-time data stream directly from the site. And in principle, you could then run your digital shadow in parallel, all the way to the digital twin, where you can in fact have, and that's part of the ideas with the FMU, FME, that where you can plug out, and you can have part of it can be the real system and part of it can be a digital model, and you can have two-way communication between your model and your physical object. But anyway, I mean, the idea of a digital twin is very interesting and promising, but from a power plant owner point of view, it is a challenge in the sense that you very rarely have the complete geometry of your object. So it's a steep curve to develop that complete digital twin of your object. maybe in the future you will require that when you are buying a new generator or a turbine, it should be equipped or supplied with a complete digital twin, but we are not there yet. And already mentioned and discussed earlier today, one of the, or many of the challenges with hydropower is it's also found in other parts of industry, but I think in some sense, some of these aspects are quite particular for hydropower, because the power plants are very are all site specific. There is no general design that's used for a large number of plants. Of course, the design rules are often the same for a large number of plants, but they are tailor-made, which means that we do not have the possibility to collect data from hundreds of identical turbines, like you can for a gas turbine or for an aircraft engine. At the same time, the equipment has proven to be very reliable, so they have a very long duration. So we do not have a fast rate of modernization, which is partly related also to what I talked about earlier, this limited amount of instrumentation. And maybe also in this, because we are in an area here where we have a very low probability in many cases. So a turbine failure is the quite low probability event. And likewise for let's say a complete failure of a stator winding or let's say also a transformer, large power transformer, but we see that the impact is very high. I don't recall exactly the figure that was, for instance, this failure at Statkraft at Svartisen, but it was around billions of kroner, not thousands. So it has a very large impact, which means that very often when we are evaluating different possible outcomes, we use this risk measure to try to quantify this, which is a product of this probability of something happening and multiplied by the consequence, or in practice, the cost of that event. And you can see this is the curve indicated on the graph is a curve of constant risk. But you can see that in some sense, these events at a very high impact or high consequence is quite different compared to the high probability events. And you can see that if we are miscalculating the probability, the risk will change much more in these high impact, low probability events. So that's a challenging when we are talking about, for instance, investment decisions. And this tool, this approach is used when the power company is deciding, should we replace that stator winding or that stator core or this runner, and small changes in the probability can have very large impact. I mean, what we are doing partially is to not only consider the end event, but try to split this up now and look more in detail on the different partial events that can happen. This is just illustrated here for as an example for the runner cracking. So instead of just will we have a cracking or not, we're trying then to look at what is at the event tree and see actually what is the probability that it will have the most dramatic consequence with the highest cost, and what is the different steps we can do to reduce that and mitigate that. But nevertheless, there is a question again, I come back to this question of, is this mechanical degradation or like thermal degradation Lyapunov stable? So I won't go into the topic of Lyapunov stability is something that comes up within dynamical systems of nonlinear systems of nonlinear ordinary differential equation, and it's this figure here is this so-called Lorentz attractor, and it's much more well known under this butterfly effect. So small changes in initial value will have a large impact on the situation where you are afterwards. And the question, Henning was mentioning this discussion that's been ongoing for a long time about mechanical fatigue, that you have this so-called threshold value. So a lot of people have argued, very knowledgeable people have argued that if you just make sure that your stresses are well below this threshold value, then in principle, your turbine should last forever. Of course, Henning was showing that, in fact, maybe long-term testing shows that it's not flat, maybe it's a different slope, but you could think that with this change, if you just below that curve all the time, you would still be able to have infinite life. My reflection, I mean, it's a statement. I don't think it's a hypothesis, but it's more just a reflection or a statement that we still have history effects. Events matters. In this case, I just indicated like an synchronization error. In hindsight, at least part of the issue causing the problem with the generator at Svartisen was an electric storm in the area that led to some very high short spikes in the overvoltages in the stator. On these other power plants back in 2001, Statkraft did some investigation, and they found that they were using these units with so-called AGC, automatic generator control, which was trying to force the way the power market is that you are bidding for a certain hour. So they're just in the switching of hours, it would sometimes force the units to outside the normal operating range. And they found that in this case that was running for 3 months, they had something like 2.5 minutes where the unit was running at 5% overload. And then they had some very short, I don't recall exactly the amount of time, but they had some short time where it's been running all the way up to about 110% overload. So then the question becomes, so can it be that some of these, even if you are well below this threshold, that we can have some certain events? You mentioned rocks also. You can think that if you take from a crack propagation point of view, that if you have an initial event that suddenly gives you a crack that is coming above this threshold line, then it will start to grow, and you will have crack development even if you are well below that threshold value. So the history effects maybe is more important than we are accounting for in these simplified models. So I'll just try to close now and raise some questions that I hope that the audience, both here physically and online, is opening up for discussion. So what is a good degradation model? But it should be for fit for purpose. That's my suggestion. But then what kind of purpose? I think we need maybe different models for concept evaluation. A lot of power companies will move now into a situation with record prices. And we are seeing maybe lasting at least quite prolonged duration of a change in the power market. So suddenly again, it seems like peak power will become much more important, and maybe then flexibility will become much more important. So in evaluating different concepts, we need some models to when we are considering, should I have 2 units, should I have 3 units, should I have 100 megawatts and 120 megawatts? Of course, there will be a cost side to this, but we need also some way to evaluate how different operating patterns will impact the choice of installation. Should I go for this full converter in the future? What is the benefit for the turbine and generator on this compared to what can I gain in terms of market operation? Production planning. So how am I using this installation that I have today in this changing market? We see there's a change in market with new type of products on the power market. These automatic frequency reserves, frequency restoration reserves, a lot of different new markets being developed, also both in the Nordic and more towards the common European flexibility market. Maintenance planning. When should I change my turbine or my generator, and what do I need to do? Can I just do how should I change my inspection intervals if I'm now changing my operating pattern? Do I need to do more frequent NDTs? And then finally, in the fleet management, if I have a large number of power plants, I might want to specialize. Some of the power plants are more suited for more frequent or more aggressive operation, and other plants are more best served by trying to serve a base load or more conservative operating pattern. And I think we might not have a tool that can be best for all this. We might have different tools for the different types of analysis that we want to use this for. Finally, I mean, the model should be understandable, or it can be very complicated to know. Of course, I mean, with this big data development and black box models, where you put in a lot of data, it might be useful, but I suspect that for a long time still we will want to, because one of the challenges with these models is that it's impossible to know what actually is driving the model. We've seen a lot of examples from other fields where this actually tuning of this large neural network can give very surprising and sometimes not necessarily the answer that we really want. And then the question comes about accuracy. Ideally, of course, we want to have a very accurate predictive model, but maybe in reality and in practical use, relative accuracy. So if you're able to distinguish between this and that operating pattern, or that you are able to say plant A is better to use than plant B, etc. Maybe that is a sufficient goal for the moment, rather than trying to predict accurately. As Vig was saying, that is it really useful to know that your turbine will fail in 23 years, and then 7 weeks and it dies. I mean, more it's better to know if it's going to. If it's very short term, it's important, but if it's far ahead, then maybe it's not so important to have this absolute accuracy. So I'll close there and then open up the floor for everyone to comment on how they see that we can continue to develop this kind of better degradation and failure models for the hydropower business. Anyone who wants to do an initial reflection on this? I'll just keep the online audience also. So Henning, you mentioned a little bit on some of the ideas that you have within Rainpower to further develop the endurance, Rainpower endurance software, and I guess methodology as well. I understand, of course, that just to get to this more fatigue data is very important to build up that that database. But do you see, let's say, just a question first, do you see this as a future product for Rainpower, or is it more just a tool or a vehicle to sell turbines?
Oh, I think it's a valuable program for the owner of the power plant to know what is the consequence. I think the main issue you talk about this absolute prediction of lifetime and the relative. And I think maybe as we see, if the new turbines, we predict a very long lifetime. So I think the partial damage, what is the cost of having this overload, having these starts and stops and so on. I think that is valuable. And if you have a fleet of turbines, you can say this one is restricted in this area, this one is more flexible. So I think this is valuable information for the producer when they buy a turbine, that they have all of this information. How can I stress this turbine comparable to the other one? So I think it's a valuable process to buy the whole system. You add a new turbine.
This program is suitable for the welding repair journal, because the repair welding during welding it will enhance the fatigue failing in times. So is it possible to use with that journal as well?
I think it's more difficult, of course, than you add something that is not perfect, and it might be that you need to measure this very carefully, but it's very difficult to also to have NDT. You need also to do the NDT for all of these regions and so on. So then you have to update the program, so we can do it, but it's of course far more complex than you do the repair.
It seems like super valuable and a very good start for predicting lifetime turbines. If I understood it correctly, this is a good base estimate for the turbine lifetime, right? Because it's optimistic in the sense that you have not considered cavitation effects, not sedimentation effects, and not resonance effects, or unknown resonance effects, maybe. So you didn't go into detail about how much the pressure pulsation amplitudes are implemented into the lifetime estimates when you consider partial degradation. Maybe you could say a few more words about that. Maybe don't want to say a few more words. We'll be interested to hear.
Yes, but as we measure on the prototype, of course, we will measure the effects of the resonance.
Yeah.
So if you have a resonance problems, we will measure this one.
Yeah.
So this will take into account if you don't apply any prototype measurements and we only rely, and also rely on the finite element analysis alone, then it's not so easy to predict resonance maybe. So that if there's a whole process with the measurements on site and all and everything, then also the resonance is taken into account. But it's true, we don't take into account the effects of the possible sediments and the wear of the runner and degradation and long time operation in water and all of these effects that and also some material defects can also escape NDT tests. You can use something there. So these effects we don't consider.
But I like
the framework. I think it's correct. I think the theoretical framework is correct. Yeah. And we can use this model and build in these failure modes. That we can increase the precision of the SM curves. We can increase the precision of the statistical models and fatigue models and so on. But I think the framework is there, which can be improved.
And of course, you could create plugins to this program, adding estimators for cavitation, estimates sedimentation effects, erosion, and then you have a fairly complete estimate lifetime for turbine and everything. And then, of course, I guess you might want to add a cost estimate plugin to this software as well, to like maybe put a cost number. So you can go to a manager and say, "This is your savings."
Well, I don't think we are the ones to add the cost estimate. I think this is more for the system. If this is a lack of in the system, there is the power company that knows the cost of this. That can add this one into the system. Yeah, you predict the time and say something about the cost.
And Erik, if you're still online, if I understand correctly, I mean, you're or the idea from Starcraft, okay, you can say that you can have plugins to Rainpower Endurance, but I guess what you are thinking about is that we can have a common kind of a hub where you are plugging in Rainpower Endurance and other models via the functional markup interface that can talk to a let's say a global model for degradation.
Yes, although some sort of not really a hub, but an environment where that would be placed in a good way. I'd say you'd have a hub or sort of an information pool that you would be able to use, some sort of a database or something. That would be a nice hub, and then you'll have these application in some worlds outside of that pool, which would then refine data points and data and make it into information and put it back into this information hub in an ideal world.
May I ask you what kind of time frame do you believe that we are talking about before you can have something up and running for let's say a test plant?
For test plant, that should be quite fast. Actually, we should ask Camilla if she's still here, because she kind of does this. Is she here? I saw her earlier. Well, no, she isn't. We're actually doing this to a certain extent now. We have some power plants that are done being modeled using the RDS standard, and the signals are done being translated into RDS and 61 and 50. And with them, we'll be able to have some automated information refinement systems that are going on. And this is just really, there are some really low-hanging fruits, just warnings for thresholds for certain values, stuff like that. Really, really simple, but it's still data processed into information. And so we're starting, we're doing our first steps now. The problem, or the real hurdle here, is to be able to structure all the information for all our plants so that these automated analysis modules can work on all our plants, and so that we can have something that's applicable to our whole park at the same time, because individual tailoring for these systems is really time consuming, and it's in general not worth the effort. But if we can do it for the whole park, then yes. So we have we've modeled 3 power plants. We still have a lot more to go, but every time we do one, it makes it easier to do the next one. And I'm not sure of the ambition. I'm not sure of our own ambition, but let's start with the most important plants, and then we'll see after that.
Thank you very much.
You have your hand raised.
Oh yeah, sorry, I didn't see that. Ole?
No, I just follow up on what Erik is saying. I think maybe we should challenge the fact that you're saying that all turbines are different from each other. Isn't there any place we can compare? Having in mind that we are using a model now, or models now, which are quite uncertain when it comes to lifetime evaluation, or remaining lifetime evaluation. I guess that comparing, for example, similar speed numbers with each other might be a possibility to start to think about, at least at this point, when you're looking at fairly high uncertainty models.
I agree.
Do you really need to say that each and one of them have to be different from each other? I don't think so. Not at this stage, at least.
Anyone who wants to comment on Ole's? From my point of view, I think that the important is that in terms of the failure mechanism, you can say that if you can have that, there you can use generic models like the rain power endurance is looking at, which is looking at generic model for fatigue. We can have generic models for cavitation or particle erosion, etc. And then you untie that with the geometry. I did as detailed as rain power is doing, but you can also start more easily with just using simpler parametric values, but at least couple the physical failure mechanism to the design. That's my personal opinion. I'm not sure. It can be different opinions, I think.
May I comment?
Yes.
So maybe it would be nice to connect this peak with the environment in the waterways, because the different environment in different waterways will have a direct impact on the turbines. So this environment connection, or the conditions that is along the waterways are very important. So there should be some kind of common research on it that links how is the condition in the tunnel and what impact we had in the turbine.
Yeah.
Because our power market is very dramatic nowadays.
Yeah.
So this is very important to be looked, in my opinion.
I definitely agree, and I think, yeah, Björn, sorry.
Just to kind of my point of view and my fear of these more specialized and high-tech solutions that as rain power endurance is that the end goal of the power producers is, at least in my eyes, to get a cost out of this. To be able to put money onto the operational procedure or plan for the turbine. And if you do that for 4 turbines in a fleet of 400, and you try to integrate that into the production planning, integrate that cost, what you'll end up with is that those 4 turbines will be run very nicely because they have a cost for operating at bad operational points, and the rest of the fleet will be run as normal. So I think it's very important that we have some sort of, and this is basically in line with what Erik is talking about as well, that we have some sort of baseline that can encompass as many turbines or as many assets in the fleet as possible, to be able to avoid the fact that you upgrade a couple of turbines with this new cost input, and you just see a higher failure rate for the other turbines because they are taking up the load for all kind of the crappy and more destructive operational points. So of course, you'll end up with at some point the whole fleet has been replaced with new and upgraded turbines, which would be a good thing in general, but it's still going to be an issue that you'll have a bias towards operating the older turbines in a worse way than the newer turbines or the turbines with the newer technology implemented for cost calculations. So that's just my kind of mindset, is that there needs to be a bench or a baseline that covers as much as possible to be able to get this to function as a fleet-wide implementation and not just a turbine to turbine implementation. Because if you implement it on a single turbine, you can't kind of take that data into the cost estimate and the production plan.
Yeah, no,
I support everything that Björn said.
Very good. We are coming to the end of this workshop. We have maybe asked more questions than we have given answers, but we have given some very good answers as well, I think, in between. I thank everyone for participating either physically or online. The first group now have the advantage of being able to have a nice lunch here. The rest of you will have to cater for that yourself. But again, thank you very much for participating, and we'll keep on getting out information regarding how we can model degradation, and we will also notify you when the recording is available online. So again, thank you very much everyone for participating.
Thanks a lot. Thanks a lot.
Thanks, everyone.
Thanks for a well-organized workshop. I think this is good for all of us. Thanks. Have a nice day, and have a nice lunch to you guys in Norway.